Hello everyone, welcome back to my channel. In this video, let us discuss about the oscillators and generators. In previous video, we discussed about Wien bridge oscillator. So in this video, we will see two more oscillators, which is a quadrature oscillator. First, let us discuss about this quadrature oscillator. So this quadrature oscillator is used because the circuit provides two sinusoidal signals with 90 degrees phase difference. So, for example, in telecommunication for quadrature mixers and single sideband generators, or for measurement purpose in vector generators or selective voltmeters. So, in these cases, we use a quadrature oscillator. So, therefore, these quadrature oscillators constitute an important unit in many communications and instrumentation systems. Okay, so as you can see here, this figure shows the first proposed quadrature oscillator circuit. So the characteristics of this circuit equation can be expressed given here. It is S cube C1, C2, C3, R1, R2, R3, R4, R5 plus S square C3, R3, R4, R5 into C1, R1 plus C2, R2 in C1, C2, C1, R1 plus C2, R2 plus S into C3, R3, R4, R5 plus R1, R2 equal to 0. We mentioned this as an equation number 1 from the circuit diagram. Okay, so as from this circuit, as S is equal to j omega, by equating the real and imaginary parts with 0, so here the oscillation condition and the oscillation frequency can be obtained as here we seen in the equation number 2, which is R3, R4, R5 is equal to C1, C2, R1 square, R2 square by C3 into C1 R1 plus C2 R2. This is given as an equation number 2, and from this uh, omega naught is equal to 1 by root over C1 C2 R1 R2. This is the equation number 3. So from here equation number 2 and 3, the oscillation condition and the oscillation frequency can be controlled. Okay, so from this figure, the voltage transfer function from V02 to V01 will be given as in the equation number 4, which is V02 by V01 is equal to minus 1 by S into C3R4. This is the equation number 4, and here the phase difference between V02 and V01 is 90 degrees. Okay, so we given is as an equation number 5. So here, by ensuring these voltages V02 and V01 to be in a quadrature, because the output impedance of the operational amplifier is very small. So the two output terminals, which we seen here, V01 and V02, can be directly connected to the next stage. Okay, so here the passive sensitives for the quadrature oscillator in this figure are all low and obtained as which we seen in the equation number 6, which is S omega naught C1, C2, R1, R2 is equal to minus 1 by 2. Okay, so this is for this circuit. And if we can see, this is this diagram as the second proposed quadrature oscillator circuit. So from this circuit, we see the characteristic equation of the circuit can be expressed in the equation which we see in the 7. So from this equation which we derived by from the figure 1, as well as we have to derive from the figure 2 also. That means this circuit, by doing the same as we done for the circuit number 1, if we done the same expression, I mean same thing for this circuit number 2, we get the equation as R3 is equal to C1 square C2 square R1 R2 by C3 C4 C5 into C1 R1 plus C2 R2, which we given as equation number 8. From this, omega naught is equal to 1 by root over C1 C2 R1 R2, which will be, which is equation number 9. So from 8 and 9, from this equation 8 and 9, the oscillation condition and the oscillation frequency can be controlled. Okay. So here from the voltages, here the output voltage transfer function from two outputs V02 to V01 will be V02 by V01 is equal to minus 1 by SC3R3. So this is the equation number 10, and the phase difference between the two voltages V01 and V02 will be 90 degrees. Okay, so by ensuring these two voltages, these two output voltages in the quadrature, the output impedance of the operational amplifier is also very small, and the two output terminals V01 and V02 can be directly connected to the next stage, as we seen in the first diagram. So here the passive sensitives for the quadrature for this figure will be low as obtained in the equation number 12. So this is for the quadrature oscillator by the two diagrams we seen here. So next, this is the experimental result for the figure 1, which by this circuit. So here the quadrature oscillator was constructed by using, that means this circuit. This circuit was constructed using LF351. By this circuit, the quadrature sinusoidal output waveforms of the circuit with C1 is equal to C2, C3 equal to C1, C3 is equal to 1 NF. Let us discuss with this. 1F and R1 equal to R2 equal to R4 equal to R5, that will be given as 10 kilo ohms, when R3 is given as 4.563 kilo ohms, and the proper power supply will be plus or minus 10 volts. So here this plot which we seen here shows the experimental result of the oscillation frequency of the figure, which was this. By variating the value of R into R is equal to R1, R2, R4 and R5, with C1 is equal to C2 equal to C3 is equal to 1 NF, and R3 was varied by R to ensure the oscillations will start. So this is the plot for this circuit. So as we can see, we also have a plot for the second circuit diagram, which will this, and this is the plot for the second diagram as same. So this is the plot, and this is the same for this both circuit diagrams 1 and 2. So this is for the circuit diagram 1, and this is for the circuit diagram 2, two plots. So next, coming to these advantages of this quadrature oscillators, it has a 90 degrees phase difference. It obtained 90 degrees phase difference because it has two sinusoidal output signals of 90 degrees phase differences are obtained simultaneously in each configuration. Okay, so next, the oscillation conditions and the oscillation frequencies are controllable, and we also have the output terminals the output terminals have the advantages of low output impedance and the high current drive capability in this. And we also have this quadrature oscillator is very simplicity, and it is low cost, and it have a passive sensitives are very low. Okay, these are the some of the advantages for the quadrature oscillator. And next, let us discuss about this VCO, which is called the voltage controlled oscillator. So what is this VCO? This voltage control oscillator, that means from the name itself, it is clear that the output is instantaneous frequency of the oscillator is controlled by the input voltage. Okay, so the oscillator, it is the kind of oscillator which can produce output signal frequency over a large range depending upon the input DC voltage what we given. So here, this is the circuit diagram for the VCO. So here in this, let us see about the frequency, how frequency controlled in this voltage controlled oscillator. So here in many forms of VCOs are generally used. So it can be RC oscillator or multivibrant oscillator or crystal oscillator type also. So however, if it is for RC oscillator type, in this, the oscillation frequency of output signal will be inversely proportional to the capacitance, as we see here, F is equal to 1 by 2 pi RC. Okay, so in this case, for example, in this case of LC oscillator, the oscillation frequency of the output signal will be F is equal to 1 by 2 pi root over LC. So we can see that the input voltage or controlled voltage increases, the capacitance get reduced. Okay, so hence the voltage I mean, this controlled voltage and frequency of the oscillations are directly proportional. So when one increases, the other will increase, okay, as well as like this. So as you see in this diagrammatical form, if one increases, the other one also will be increases in this voltage controlled oscillator. So here this figure represents the basic working of a voltage controlled oscillator. So we can see that the nominal controlled voltage represented by VC in NOM, that means nominal. So the oscillator works as its free running or a normal frequency, that means FC, that is the normal frequency. And as the control voltage decreases, the nominal voltage and the frequency also decreases. As the nominal voltage increases, we see that the frequency also gets higher in this diagram, in this plot. Okay, so here the diodes which are variable capacitance diodes. So these are implemented for getting this variable voltage. So for low frequency oscillators, the charging rate of capacitor is altered using controlled current source to get the variable voltage. Okay, so in this VCO, there we have two types, which is a harmonic oscillator and relaxation oscillator. So this harmonic oscillator means the input of the waveform produced by harmonic oscillator is a sinusoidal. Okay, so this can often referred as a linear voltage controlled oscillator. So the examples for this LC, the examples are LC and the crystal oscillators. Okay, by these harmonic oscillators, the examples are LC and the crystal oscillators. So in this, the capacitance of the uh, the capacitance of the diode is varied by the voltage which is across the diode. So in this in turns I mean this in turns the capacitance of the LC circuit. Okay, hence the output frequency will change. So the advantages of the frequency stability with reference to the power supply, noise and temperature, accuracy in control of frequency also. So here the main drawback is this type of oscillators cannot be implemented effortlessly on monolithic ICs. Okay. So coming to these relaxation oscillators, here the output waveform produced by the harmonic oscillator is the sawtooth. Okay, so this type can be given a large range of frequency using a reduced quantity of components. So mainly it can be used in monolithic ICs. So here the relaxation oscillators can process by delaying based ring VCOs or grounded capacitor VCOs or emitter coupled VCOs also. So in coming to this delay-based ring voltages, I mean VCOs, here the gain stages are attached together in a ring form. So as the name implies, the frequency is related to the delay in every single stage. Okay, so here the second and third type VCOs, that means grounded capacitor VCOs and the emitter coupled VCOs works almost similarly. So the time period taken in each stage is directly related to the charging and the discharging time of the capacitor. Okay, so let us see about this working principle of VCO, that means voltage controlled oscillator working principle. So this VCO can be designed by means of many voltage controlled electronic components such as diodes, transistors, operational amplifiers, etc. So here we are going to discuss about the working of the VCO using operational amplifier circuits. Okay, so this is the diagram for the VCO by using operational amplifier. So here the output waveform of this VCO will be a square wave. Okay. So as we know, the output frequency is related to the controlled voltage. So in this circuit, the first operational amplifier will function as an integrator. Okay, so here the voltage divider arrangement is implemented here. So because of this, the half of the controlled voltage that is given as an input is given to the positive terminal of the operational amplifier 1, which we seen here. So the same level of voltage is maintained at the negative terminal also. So this is sustained the voltage drop across the resistor R1 as the controlled voltage. Okay, so here when the MOSFET is in on condition, the current flowing from the R1 resistor passes through the MOSFET. Okay, here the R2 have the half of the resistance. Same voltage drop and twice the current as the R1. Okay, so the extra current charges are connected by the capacitor. So here the here the operational amplifier 1 should provide gradually increasing the output voltage to supply this current. So when the MOSFET is in off condition, what happened is the current flowing from the R1 resistor passes through the capacitor and it gets discharged. Okay, so here the output voltage obtained from the operational number 1, and that is operational number 1 at this time will be falling. So as a result, the triangular waveform is generated as the output. Okay, from this operational number 1. So what happened to this operational number 2 is this operational number 2 operate as a schematic trigger. Remember, operational number 1 is works as a MOSFET, and this operational number 2 is operate as a schematic trigger. So here the input of this operational amplifier is a triangular wave. Uh, the first one it will be as a square wave, and here we have a triangular wave, which is the output of the operational output of the also operational amplifier. So if the input voltage is higher than the threshold level, the output from the operational amplifier 2 will be VCC. Okay, so if the input voltage is less than the threshold level, the output from the operational amplifier 2 will be 0. So therefore the output from the operational number 2 will be a square wave. Okay, so let us see some of the applications of VCO. This VCO can be used in a function generator, phase lock loop. It is also used in a tone generator as well as a frequency shift keying, and also in frequency modulation. These are some of the applications used by the voltage controlled oscillator. So coming to the next topic, let us discuss about this sawtooth wave generator. Here this sawtooth wave generator means a linear non-sinusoidal triangular shaped waveform represents a sawtooth waveform. So in which fall time and raise times are different. Okay, so here a linear non-sinusoidal triangular wave shape waveforms represent a pure triangular waveform in which fall time and rise times are both are equal. So here the sawtooth wave generator is also known as an asymmetric triangular waveform also. So here we can see the graphical representation of sawtooth waveform in this figure. So the general applications of this sawtooth waveforms are frequency or tone generation, sampling, modulation, etc. also. So here here the non-sinusoidal waveform is nothing but a sawtooth waveform. So because of its teeth, that means the waveforms looks like a saw, so it's named as a sawtooth waveform. So in an inverse, that means in a reverse sawtooth waveform, the wave suddenly wraps downwards and rises sharply, as you can see here down. So from this from this, a conventional sawtooth can be constructed by using this equation. X sawtooth is equal to a by 2 minus a by pi. Sigma k is equal to 1 to infinity sine into 2 pi kft by k. So where here a is the amplitude of the generator of this equation. So by using fast Fourier transform, this summation can be calculated more efficiently. So in the time domain, the waveform is digitally created by using a non-band limited form. Okay. So coming to this sawtooth waveforms generator, we using a 555 timer as well as an operational amplifier also. So let us discuss about this working principle of a sawtooth wave generator by using a 555 timer. First, let us see about this 555 timer. So this is the diagram for the 555 sawtooth wave generator using 555. So here sawtooth wave generator can be constructed using this transistor and a simple timer, that means 555 IC. As shown in this diagram. So it consists of a transistor, a capacitor, a Zener diode, resistors from a constant current source that are used to charge the capacitor. Okay, initially just assume that the capacitor is fully discharged. Okay, so what happened is the voltage across the capacitor will be 0 and the 555 output is high because of the internal comparators connected to the pin number 2. Okay. So here the capacitor starts charging to supply voltage because the internal transistor of the 555 shorting the capacitor to ground and it opens. So during charging, the 555 output goes low if the voltage increases about 2/3 of the supply voltage. So during this discharging, the 555 output goes high if the voltage across C decreases below one-third supply of voltage. So here, hence the capacitor charges and discharges between two-third and one-third of the supply voltage. Okay. So, but the disadvantage here is that it requires bipolar power supply. So, by this the frequency will be given as by this the frequency will be given as F is equal to VCC minus 2.7 by R into C into VPP. Okay, I didn't mention the frequency here, but remember F is equal to VCC minus 2.7 by R into C into VPP. Here where VPP is a peak to peak voltage, output voltage. Okay, so VCC is the supply voltage. So to get the required frequency value, select the proper values for the VCC, VPP, R and C. Okay. So now let us see about the sawtooth wave generator by using this operational amplifier. So this is the diagram for the operational amplifier sawtooth wave generator. So here a sawtooth waveform is used in the pulse width modulation circuits and the time-based generators. So here a potentiometer is used when the wiper moves towards the negative voltage, that means minus V, then the rise time becomes more than the fall time. Okay, so when the wiper moves towards the positive voltage plus V, then the rise time becomes less and less than the fall time. Okay, so here when the comparator output goes a negative saturation, what happened is the negative voltage is added to the inverting terminal. So thereby the wiper moves to the negative supply. So this causes a decrease in the potential difference across the R1. So here the current through the capacitor and the resistor will be decreased. Okay, so this is the plot for the sine wave, plot for the sawtooth wave using the operational amplifier. So here is the slope decreases and rises the time. Here the slope decreases and the time also decreases. As you can see properly, here the slope decreases and the rise time also decreases. So when the comparator output is under positive saturation, the potential difference across the R1 increases and the current through the capacitor resistors also increases. Okay, so this is due to the presence of the negative voltage at the inverting terminal. Then when the slope increases, then the fall time also when the slope increases here, the fall time decreases and the output obtained as a sawtooth waveform. Okay, so let us see about some of the applications which is used in this generator. So applications are this sawtooth waveform is the most common waveform used to create sounds with subtractive visual and the analog music synthesizers. So it is used in music. So sawtooth waveform is used in music. As well as this sawtooth wave is the form of horizontal and the vertical deflection signals that are used to generate a raster on the monitor screen or in the CRT based television also. So these are some of the applications for this sawtooth wave. So next, let us discuss about this square wave generator. Okay, so this square wave generator means it is defined as an oscillator that gives the output without any input. So without any input means we should give input within 0 seconds. That means it must be an impulse. It must be an impulse input. Okay. So this generator is used in a digital signal processing and electronic applications. So here the circuit wave generator is also known as an stable multivibrator for a stable multivibrator or means free running, and the frequency of the square wave generator is an independent of the output voltage. So here we are seeing the basic circuit diagram for this working of the square wave generator. So here to design this square wave generator, we need a capacitor, resistor, and operational amplifier and the power supply. So here the capacitor and the resistor are connected to the inverting terminal of the operational amplifier, and the resistors R1 and R2 are connected to the non-inverting terminal of this operational amplifier. So here the circuit diagram which we seen here. So in this if we force the output to switch between the positive saturation voltage and the negative saturation voltage at the output, of this op amp, we can achieve the square wave as an output wave.